when we are talking of optimum base chemistry, then what we are telling is in the higher carbon equivalent in ferritic grades, that means grades like say 0.03% carbon, or say silicon steel, or say 430 stainless steel, these are ferritic solidification. So what happens in ferritic solidification? Solidification is totally through ferritic mode. Even after completion of solidification, delta ferrite continues and delta to gamma transformation in solid state takes place at much lower temperature. So what is the issue here? Issue here is first the solid shell, which is delta ferrite, is relatively soft. I have told you the high temperature strength of delta ferrite is much less, maybe about 20% or 15% of that of high temperature strength of austenite solid shell. So this for ferritic solidification, the issue is soft ferrite, which is creating the problem, which might create problem. There might be crack formation because it cannot withstand the your ferrostatic pressure and things like that. Another issue is because the delta to gamma is taking place at much lower temperature, there is a possibility of delta grains of delta growing to a quite big size. So delta, if the delta grain size are big, then also it is not a desirable situation. The problem of crack formation is also there. So there, this restriction of this growth of columnar grains of delta, initial solidification is only columnar, I have told you. So you can control the growth of the columnar grains by how? By adjusting the carbon equivalent, that means the chemistry, that means you are increasing slightly the carbon equivalent, you are increasing in stainless steel family slightly the nickel equivalent by chromium equivalent. So by that process you are trying to induce delta to gamma at higher temperature. It is normally at very low temperature, much below solidification completion. So you are allowing, and the for this type of grades the solidification end temperature is quite high, maybe at 1400, maybe 1450. So that means delta is remaining at high temperature during cooling for quite some time. That means there is a scope for increase in delta grains, delta columns, columnar grains of delta. So this delta to gamma transformation in solid state can be brought up. That means that incidence of delta to gamma transformation can take place at higher temperature if you slightly increase carbon equivalent. How do you use carbon equivalent? You can use slightly carbon, you can use slightly nitrogen, you can use slightly manganese. All these are in the carbon equivalent, positive elements in the carbon equivalent, because they are strengthening the austenite rather than the ferrite. So austenite formation will be enhanced by using slightly higher carbon equivalent. Whatever I am telling is of course within specification. You cannot go to a carbon or nitrogen or manganese which is beyond specification. Obviously you should not do that. Within specification, whatever possibility is there, you can slightly adjust it. That means for very much ferritic grades you slightly increase carbon equivalent, that is the solution. But in a peritectic grades like when the carbon equivalent is around 0.1 or nickel equivalent by chromium equivalent is around 0.55 for ferritic, for stainless steel family. So there what you have to do? Here the solution was slightly increasing carbon equivalent, but for the peritectic grades the solution is slightly lowering the carbon equivalent or lowering the nickel equivalent by chromium equivalent in stainless steel 304 grade, which I have just discussed few minutes back. So thereby what you do? You avoid this delta to gamma transformation in brittle temperature zone. Here delta to gamma is taking place in the solid area, in delta area only, and at quite high temperature. If it does not take place at high temperature, then what happens? Delta grains will continue to grow. So you have coarse columnar grains that might create, and if the superheat is also high, that means the columnar grains will be quite coarse, they will be extending from the surface towards the center of the cast product. There might be breakage of slab or bloom, this we have observed for ferritic stainless steels or say silicon steels or very low carbon steels, because of soft ferrite and the ferrite columnar grounds of ferrite extending almost towards the central region. So, here the solution is slight increase in carbon equivalent for ferritic grades. For peritectic grades, which is having a chemistry carbon equivalent around 0.1, or for stainless family the nickel equivalent by chromium equivalent is around say 0.5, slightly higher than 0.55, maybe 0.56 or 0.7. So, there what we do, we lower the carbon equivalent, so that delta to gamma transformation does not take place in this brittle temperature zone. So, depending on the grade, we have to make some adjustment in chemistry, minor adjustment in base chemistry within specification of course. Then I have talked about the effect of residuals. What I have talked about in peritectic grades, I have mentioned that we have very coarse austenite grains. Why austenite grains are coarse? Because of depression formation, the heat transfer in the mold is affected. Because of that, the cooling rate, the casting rate also comes down. Because of that, the austenite grains become quite coarse, and if the austenite grains are coarse, then what is going to happen? The grain boundary area will be less. I think you appreciate this. If the grains are finer, the grain boundary areas are relatively more. If the grains are coarser, the grain boundary areas are relatively less. So, if you have coarse austenite grains, then what is going to happen? The grain boundary areas are relatively less, and then this formation of aluminum nitride or niobium nitride or vanadium nitride, I have talked about this. When this happens, when this precipitation of aluminum nitride, vanadium nitride or niobium nitride, when do they form? They form around say 800, 700 degrees centigrade. So, if you have a coarse austenite grains, the boundary area is relatively less. So, the precipitation density at the boundary areas will be relatively more. If the boundary area is more, same amount of precipitation will lead to relatively less density of precipitation. But if you have coarse austenite grains, means the boundary areas are relatively less. So, the same amount of precipitation you have high density of precipitation, and this grain boundary areas become brittle. So, that is why this particular temperature range I have mentioned earlier, around 700, around 650, around 750, this is again a low temperature brittle zone. So, we have to avoid this zone, we have to avoid formation of this nitrides. So, what is the way out? Your nitrogen has to be low, aluminum has to be low. Normally we do killing with aluminum, but for that we need only maybe 0.2 aluminum, but sometimes people use more of aluminum. So, unnecessarily you have more aluminum in steel, which might create problem, this type of problem in peritectic grades, in grades which are having about 0.1% carbon, or in grades like 304 austenitic stainless steel. So, we have to be careful about peritectic grades. We must have lower nitrogen, aluminum, and we have to be careful about microalloying elements like niobium and vanadium in these grades. Then I have talked about austenitic solidification grades, where the solidification is taking place totally through austenitic mode. So, what is happening there? There we must have lower phosphorus, sulfur and higher manganese by sulfur ratio in austenitic grades. I have given you example of AISA 310S is austenitic solidification. So, if we can reduce this phosphorus sulfur, the incidence of defects, intercolumnar cracks in slab is much less. So, for such type of grades, control of phosphorus sulfur and higher manganese sulfur assume still higher importance. So, it is very important there. It is important in all grades, but it is very important in austenitic grades. We must control phosphorus sulfur and use higher manganese by sulfur in grades of austenitic solidification. What are these grades? In normal carbon steel or low alloy steels, these grades are having carbon content of say around 0.25, 0.3, 0.4, 0.5. More the carbon, more is the austenitic solidification, more problems of microsegregation. So, we have to must have low phosphorus, low sulfur and higher manganese by sulfur ratio, because the shell thickness is an issue here. If the shell thickness is less because of high microsegregation, they cannot withstand the pressure from ferrostatic pressure. So, there will be a crack formation. The central segregation is also a problem. The central segregation is a problem in general for all grades, but it is quite prominent. Extent of the problem is quite high for austenitic solidification grades. So, I have mentioned about to you about mechanical soft reduction, which can take care of this to certain extent. So, that will come under the continuous casting parameters, use of mechanical soft reduction, but as far as residuals is concerned, it has to be low. So, what are the strategies then? First, we understand from the chemistry how the solidification is taking place. That is the first requirement. If we know how the solidification is taking place, then we can know whether it is a whether it is a, if it is a ferritic or either ferritic or austenitic type of solidification, that means the two extremes in the chemistry range, then we know that these are sticking type of grades, these are bulging type of grades. So, that is one type of solidification characteristics, and if the chemistry is around 0.1% carbon equivalent or is around 0.55 nickel equivalent bichromium equivalent for the stainless family, then we know that those type of chemistries or grades will indicate depression, surface depression, whether longitudinal or transverse. So, if you understand what is the solidification characteristics, then we can understand or know what is the type of solidification characteristics, whether it will be depression prone or it is a sticking prone or bulging prone, and understanding that, then we can devise the casting parameters accordingly. As I mentioned, if it is a sticking grades type of grades, that means for very low carbon or very high carbon, the mold slag should have better lubrication, because here the lubrication is the issue, because it is a sticking prone grade. So, what is sticking? The shell will try to touch the mold. Therefore, the mold slag which is present in between the mold surface and the solid shell, it must resist that. So, the lubrication has to be better there. Accordingly, you can you can use different oscillation characteristics. I have told you, when this sticking is the issue, then we have to be careful about better lubrication. The friction between the mold surface and the shell surface has to be controlled, otherwise there will be sticking, there will be lot of surface defects, and there might be breakout formation. But if you have depression grades, if you are casting depression grades which are peritectic grades, what do? There heat transfer is the issue. Depression is the main problem. Why is this problem? Because this delta to gamma transformation is taking place in the brittle zone when the solid fraction is between 0.9 to 1. So, there what you do? You have molds, you use mold slag which has characteristics of lower heat transfer. So, the heat transfer is the issue there, unlike sticking grades where the lubrication is the issue. So, you see, depending on their behavior, solidification behavior, how they behave during continuous casting, we have to use our casting strategy accordingly. Again, I have told these grades, the sticking type of grades, the sticking is taking place within the mold. Below the mold, same grades will show bulging tendency. So, that means you have to control bulging in very low carbon and ferritic grades. These are the grades which indicate sticking tendency. The same grades will indicate bulging tendency below the mold. So, there the secondary cooling has to be such that the temperature of the solid shell is brought down relatively faster, then only you develop the strength of the shell, because it is delta ferrite, the strength is low. So, the low solid shell is prone to crack formation. So, therefore, you use slightly higher secondary cooling and uniform secondary cooling. Gradient of secondary cooling is important. Do not use suddenly high and suddenly low, that might create temperature gradient. It has to be uniformly coming down from top to bottom of secondary cooling, but relatively the intensity has to be slightly more for this type of grades where you have bulging, then only you can resist crack formation. And so, the three strategies, either selection of continuous casting parameters based on their what is their characteristic. So, grade specific, we call it grade specific selection of continuous casting parameters, or you use optimum base chemistry, I have again mentioned, depending on whether it is depression grades, that means where the carbon equivalent is around 0.1. So, what you do, you slightly increase, slightly rather decrease the carbon equivalent, so that you can avoid delta to gamma in the brittle temperature region. So, thereby you can control stress generation, additional stress generation from delta to gamma transformation in towards the end of the brittle temperature region. This is the brittle temperature region. So, if you can avoid delta to gamma in this region, your depression tendency will be less. That is what you do by using lower carbon equivalent, or as I have shown you, given the example, by decreasing the nickel equivalent by chromium equivalent to a value which is lower than the 0.55, which is the start of the peritectic chemistry. If it is lower, at lower value of the peritectic chemistry, so the delta to gamma transformation takes place at lower than the solidifying completion temperature. That means when the brittle temperature we can avoid. So, this is the strategy which we had opt. So, either you use the base chemistry within specification, adjust it accordingly to take care of the particular solidifying characteristics. For ferritic grades you use higher carbon equivalent, I have mentioned why, and for peritectic grades you use lower carbon equivalent. Of course, within specification, I am again and again telling, within specification whatever range of chemistry you have, within that you can make some adjustment, minor adjustment, so that you can avoid this brittle temperature zone for peritectic grades, and you can have delta to gamma transformation relatively at higher temperature and restrict growth of delta ferrite columns, delta ferrite columnar grains. So, this is a strategy which you adopt. Minimum residuals of course is required for all grades, but for certain grades it is more pertinent. Which are the grades? Either in peritectic grades you should have lower nitrogen or aluminum to avoid formation of aluminum nitride or micro nitrides or microalloyed microalloying elements like niobium nitride or vanadium nitride at the coarse austenite grain boundaries I have told you, which happens in peritectic grades, which is a problem in peritectic grades because of surface roughness. Because of the surface roughness, heat transfer is slightly lower, and because of that you have coarse austenite grains, and because of that the grain boundary areas are relatively less, and the density of these precipitations, aluminum nitride will precipitate in all grades, but if the grains are coarse, austenite grains are coarse, then the density of aluminum nitride precipitation at the grain boundaries is relatively more for coarse grains, because grain boundaries are less. So, that is why this is a problem for peritectic grades where the grains are relatively coarse. So, we have to be careful about this. And then as I have told you, phosphorus sulfur and manganese bisulfur has to be low in all grades to control microsegregation, but this is particularly important for grades where austenitic solidification is there. So, there you have to be more careful. So, these are the three broad strategies one should follow, either selection of casting parameters, after understanding the solidification characteristics. So, we call it grade specific selection of casting parameters. We know how a particular grade will behave during solidification, accordingly we decide the casting parameters. Then we know the broad how the broad grades the grades will broadly follow the solution pattern. Accordingly, we adjust the in small amount we adjust the chemistry within the specification to take care of the problems. I have given several examples of this. Then of course, residuals you have to control whether it is phosphorus sulfur and manganese by sulfur ratio for controlling segregation, or for avoiding the brittleness at around say 700 degrees centigrade, in particularly for the peritectic grades where the austenite grains are coarse. So, we must have relatively lower nitrogen and aluminum in these grades. Unnecessarily high aluminum we should avoid and try to use lower nitrogen. We try to control nitrogen. I mentioned earlier that nitrogen is a residual, we do not want high amount of nitrogen unnecessarily in any grade. So, again control is very important. So, these are the strategies one should adopt to enhance the quality of steel cast product, and if the quality of the cast product is good, then for the rolled product, that means after rolling you have a good quality on the surface. I think I have covered most of the issues related to the quality of cast product. Thank you very much.